All right, so let's just jump in. What is reproducible science? So by way of background, I think it's important to highlight that somewhere around 10, maybe 15 years ago now, there emerged this idea that the science that the collective group of scientists were doing, whether it's in psychology, medicine, biology, chemistry, work couldn't be replicated. It couldn't be reproduced for one reason or another. It could be because the methods were, oh, we did stuff with 5 rats and then now here's some results. Or, well, we brought people to the lab and we put them in front of a computer and we didn't describe what computer or what software in enough detail. And so people are reading between the lines, guessing a little bit in the method sections. And so when it comes time for them to replicate that work, we're not finding the same results. And so a lot of this crisis exposed we need to do better, and we need to do better with respect to documentation, code-based programming for analyses, and often even pre-registering our analyses. So saying ahead of time what we intend to do rather than saying what we're going to do when data is in hand. And so at a high level, there's a set of papers that I encourage you all to read whenever you have some time, and they go into this problem in great excruciating detail across, again, fields like medicine, but also psychology. Some of this work is essentially showing that part of the reproducibility problem is not exclusive to psychology, but we do tend to suffer the most. And so if anything, that's why I found it most important to share with a group like you all that there are things that we could be doing to enhance the chances that someone can replicate our work. Stephen?
Did you get interested in this because of video game literature and the reproducibility of that data? I started reading your old, looking at your old papers. I was like, oh my gosh, that's probably why you got into this.
That's kind of exactly where it started. So my graduate advisor was Dr. Wally Boot, worked with Dr. Dan Simons. Dan Simons is one of the early champions of open science psychology. And so working, with those folks, it became an ongoing conversation to the point where everything we wanted to do together, we wanted to pre-register. And so I got an opportunity to learn that process. I also got a chance to be a part of a multi-site replication, I think for psych science, where they said, here's some code, here are the scripts, all of you across, I think it was like 50 or 60 labs, now run this, export the results, give us those, and we'll do kind of a meta-analysis across everyone. And that was the most inspiring exercise because it showed me that if you think about it enough, you can be organized enough to work with 60 labs. And it really all starts with the materials that you hand off. And it also started with a lot of Python code. So that was also kind of where I got into Python and found how helpful that could be to kind of support the open science mission. But yeah. So, again, what is reproducible science? A lot of you hit on these points already. They include things like making the entire scientific process transparent. And I say as allowable because you might run into situations where you're working with very private, medical data. Obviously, you can't open source that. Or you might be working on a specific grant that has certain conditions in your contract that don't allow you to openly share, but rather just share with that agency. And so I think what I'm describing here today and throughout the rest of the days of the workshop has that caveat that you might end up doing a grant or working with an entity that has certain rules that might not allow this to happen. And so that's just something for you to think about. I think largely it's because, if you're working, let's say, with the military, there could be confidentiality or national security issues at play. And so that's the why you cannot make this data available openly. But a lot of funding mechanisms like those provided by NIH are now almost requiring this. So I'm part of a large group that does research in the Bronx. We have samples of 700 older adults. We follow them for 5 years. And in that mechanism and that funding mechanism, we're actually required to make our data as openly available as possible. So we host some of it on public-facing repositories. We have data use agreements and concept proposal processes where people can apply to use our data. And so in general, that's the future we're heading into. We should be heading into a situation where everything we do should be auditable. And so at a high level, that's part of what reproducibility means. So that's sharing the experiment code, sharing the raw data, sharing the analysis code, so that I can go from start to finish, from data collection through data analysis, and I can see every piece of code that got me there. But it's not just code. This is also things like writing a really good method section. Sometimes that means that you might want to list the model number of the monitor because maybe that matters. And maybe you don't realize it matters until 10 years from now when somebody writes a meta-analysis and you realize these low-level factors matter. And so it's thinking of all the important details that you did in your experiment, but also all the important details that, or sorry, all the less obvious details that are as equally as important, like monitor details or device hardware. If you're running on like a gaming PC, like what specs does that PC have? It all has bearing onto the experience that the person had. So anyway, that's one way of being reproducible. Another way is sharing stimulus sets. So if you, for example, ran an experiment on emotions and you gave, let's say 50 angry faces and 50 happy faces, maybe you want to open source those and make them available so that when someone else wants to replicate that work, they're not generating a brand new image set that might have its own artifacts or special features. Kind of went over this one already, but I'll say it again because it's so important. Being able to walk from start to finish in code. So you have raw data, it's sitting in a folder, and I should be able to hit play and get the same output every single time. That's at least what reproducible science is meaning to me nowadays. Related is this idea of the FAIR principles. So just by a show of hands, have you ever heard of the FAIR principles in any of your courses before? No? Okay, so we'll get into them in just a few slides, but at a high level, findable, accessible, interoperable, and replicable. Sorry, I always forget the R. But at a high level, these are principles that govern how you should think about your data and the formats you should supply your data in. So we'll get to that soon. Now, with respect to pre-registration, I'm curious, how many of you have pre-registered your studies before or have colleagues that have pre-registered a study? Okay, so a couple people. So in general, pre-registration starts off with a clear idea of what you intend to do with your data once you have it. Often what that means is that you need to pilot your experiment and have a sample file to work with. And so your pre-registration process starts as early as piloting, and it should be, so to speak, finalized before any real data is collected, because at that point, you're still agnostic of any understanding or anecdotes that a participant might have given you. And so you're pure in the sense that you've not been contaminated with all those confounds that might bias your analysis thinking. So when you pre-register your study, you might specify your exact hypotheses and the exact variables. You might specify the exact modeling approach and model syntax. And so then when your data is in hand, let's say 6 months from now, you just download it, run it through the script, and then you're done, at least as far as your pre-registered analyses. You'll run into situations where a reviewer might say, hey, I want to see an analysis on X, Y, or Z, and it wasn't in your analysis plan. That's an opportunity for you to be explicit and maybe say that in your manuscript. These are the pre-registered analyses, and these are reviewer recommended or exploratory. And so that's one way to work through that concept of pre-registered hypotheses. Sometimes they are fully specifiable early on, and sometimes you have situations where you have to conduct a new analysis at the behest of a reviewer. It happens, and it can be a frustrating experience, especially if you've gone through all the trouble of pre-registering everything. Now, the benefits of reproducible science are probably obvious, but I'll just highlight them here. It increases the likelihood that the research will be correct or that the results are quote unquote true effects. Reproducibility obviously also makes it easier to check the research. If you do something and I want to understand how you did it, I can download your data, download your code, hit run, and have the same spreadsheet that you ended up with. And then along the way, I can learn different mathematical operations or data transformations that might be helpful in other lines of research. And then the rest are things that are maybe even obvious, like, well, if you have code that does a certain action, it'll probably also apply to other projects that have similar data structures. So there's a lot of benefits to reproducible science, and including for yourself. So, when you're developing your own lab as a new faculty member, it's important to have tools that your students could be using that allow you to all be on a common understanding of certain like mathematical formulas. So like, for example, in our lab, we have an R package, and it's how I communicate with Gabby. Hey, here's an update to my API endpoint, or hey, Stephen, here's how you calculate something from a DICOM image, rather than have to send everyone individual functions and like not know how they're being upkept with respect to version control. I can put all of that in a package or a Python library and reuse it across a lab, or eventually make it public and allow anyone to reuse it in their research. Now, with respect to reproducibility and replicability, I just want to point out that there's a subtle difference. Reproducibility is more so the idea that you can get the exact same results if you had all the pieces. So the original data, the original code, the way that you ran the experiment, who knows, maybe even the monitor that you used. But then replicable is more so at the scientific level. Conceptually, are you getting to the same place? If processing speed is affected by stress, and I measure processing speed and stress one way and you measure it another, we should still end up with the same conclusions, that stress makes people slower, or maybe even in some cases faster, at solving some kind of speeded problem. And so that's just a subtle difference that I wanted to make sure I highlight before we get too far. Now, a lot of these concepts are propagating through the research enterprise. And recently I had an opportunity to learn about the Equator Network. Just curious, has anyone heard of Equator Network before, or some of these guidelines for publishing? Okay, so in general, they end up being like checklists where you might want to be sure that you specified details like how participants were compensated, or how you went about IRB approval, what's in your protocol, all the way down to, did you make sure you had a statement about ethics on the title page, or did you make sure that you listed your conflicts of interest? And so it's all things that we over time learned to do, but they've now been formalized into lists that now some journals are requiring you to upload. So I'm recently working on a paper related to people's willingness to provide various sensor data for health research. And in publishing that work, I was required to put together one of the Equator Network checklists that documents exactly where I made certain assertions, or where I talked about a specific aspect that should be reproducible. So it'll say something like, list the page number and paragraph where you listed the number of participants. And so you need to not only make sure you write it in your manuscript, but then you need to reference that page. And then maybe the frustrating part that I'll just share candidly, you're editing your manuscript, pages change, you need to update all that manually. And so that's where this is something best done at the moment right before submitting, and not when you're still iterating and editing. So just something that's, I think, on the horizon. Some journals are requiring it, some journals are making it optional. My guess is 5 years from now, these will likely be required across most journals. They have different checklists for different types of studies. And so that might be where some journals might require, at the very least, something for an observational study, and then something different for a clinical trial. So it's not like you can learn this checklist format and be done and apply it to all your other papers. You need to kind of pick the flavor of the checklist that matches your type of study. So I see this as kind of a long-term learning exercise, learning what's expected and getting yourself into the habit of doing that from the get-go, rather than, upon submitting. So anyway, just highlighting trends in open science, trends that I think will become the standard, probably in the next 5-10 years. Before I continue to the next section, are there any questions, anything I can clarify? Okay. So this next section is where we start to go over some of the specifics with respect to reproducibility. I promise we're getting to our code soon. I'm just kind of working through the story of why this is so important. Now, with respect to reproducible workflows, one of the things that I'd like to say is that in general, these are documented code-based workflows that start with raw data and the folders that you should be dropping off your raw data, all the way through where your data should be exported, and all the code that went from start to finish. Part of this is almost as simple as how you organize your folders. This book here in particular has like a recipe. Like for most projects, if you follow this recipe, this is a blueprint. You don't have to creatively think about it, although you could. If you follow this style, it just fits. And so part of that reproducible workflow is, creating that pipeline of folders and code, and maybe some markdown documentation. But part of it is also then how you version control that code and those pipelines. So one way that I do this is with Git or GitHub. And in just a bit, we'll go over a demo on how to use GitHub. In general, what I'd like to say is that GitHub allows you to know exactly when and where a change was made and by who. So like, for example, if Gabby changes like one letter in her code, like I would see it, I would see it as a difference between the last upload of the code and the new upload. So it's a little bit different maybe than like word track changes, although conceptually it's doing the same thing. So we'll get more into that in a few slides. Now, at a high level, this is what a typical data science workflow looks like, and you all are already doing this in your own work. As I've seen in various presentations, you start off with, well, actually, I'll start off with a funny anecdote. This model actually doesn't have the data collection piece, and I think if anything, it's the most important. You can have the entire circle box be reproducible, but then you have like a black box with respect to data collection, so you have a blind spot with respect to your reproducibility. So I, so to speak, updated it for this workshop to say the typical data science workflow and reproducibility approach should start with data collection. From there, you have to import your data to do stuff with it, whether it's in Excel or SPSS. You then have to tidy it. And so by that, I mean, add new columns, reformat columns, strip out certain variables or pieces of text. And then from there, you have an almost visual, an analysis ready data set that you can either transform some more, visualize, or model, with the final goal of eventually communicating those results in some form of presentation or formal report. With respect to tidy data, this is going to come up a lot, so I wanted to just make sure this concept was clear. Tidy data is every column is a variable, every row is an observation, and every cell is a single value. If you've ever seen an Excel spreadsheet that has like 4 headers where they're like broken out with merged cells, that is not tidy data. And I say that because that's how I used to structure my data, and it was amenable to doing a lot of things in Excel. And the more I started to use code-based approaches like in Python or in R, I realized that that just doesn't work. It doesn't make it easy to query your data when you have these nested headers that aren't easy to crawl through with code. So I wanted to just say again, tidy data is a format that looks like this, a tabular, rectangular data format. Obviously, there could be missing data in here somewhere, and it's still tidy data, but if you have multiple headers, it is not tidy data. So now, with respect to unclean data problems, there are many, and this is not an exhaustive list, but this is just some of the most important problems that you might run into. I'll start by saying that if you had a hand in designing the data system, you likely wouldn't design it in a way that generates untidy data. You would design it to generate tidy data from the beginning. But we're not always in that driver's seat of control when designing or working with data. So we often just need to take what we get. And so in practice, normally what we need to first do is determine data structure issues like column headers that are values and not variable names. So somewhat of a transposed data set, multiple variables stored in one column. So this is a fun one always, where you have code like, I don't know, image 1.png and then color. And that's all in like one cell. And so now you need to like expose that into multiple columns. That's a problem, but it's easily solvable with code, especially if your data is in JSON format like that. There's also a problem where you can have multiple observation units stored in the same table. So imagine you had one version of the experiment collected something in Celsius and one in Fahrenheit. They're both stacked, and you forgot to add a column that says Fahrenheit and Celsius. That's a problem to fix. And that tends to be pretty common if you're working with sensor data from companies that work in multiple regions. So I work with some folks that give me air pollution data. And if I'm taking some air pollution data where the person set up the app in metric, I have one format, and to set it up in imperial, I have another. And I can't just cleanly stack them. I need to first see which format they're in, then stack them, then apply the appropriate metadata. And so sometimes this is an issue. And then there's also data quality issues like values out of range. If you're talking about image data, it should be between 0 and 255, because that's just the way that color space works. But if you have a value of like 5,000, that's out of range and it won't be represented appropriately in an image. You can also have improperly or inconsistently coded response options. So imagine you have a survey and you have a question that or something along the lines of like strongly agree, strongly disagree. Let's say that's repeated 2 times. And let's say that when you set this up in Qualtrics for the first 10 participants, this was coded as 0. And then in the later set, you realize you made a mistake and you recoded it to 5. So now you have 2 recodings of the same variable, and you need to apply a new recoding scheme to get it back to all the data matching one coding scheme. And then another frustrating problem is that you can have multiple columns with inconsistent missingness. So you have more records in, let's say, the age column than you do in the education column. So not everybody has an education value. Everyone provided me an age value. And if I needed to use both for an analysis, I can't. I need to make some concession, whether I drop cases list-wise or I keep people that at least have one value. And so these are all data problems to deal with. Now, we talked early on about the FAIR principles, so I'll just highlight them here. The first one is that the data is findable. It's the case that it's not just about making it open, it's making it open with the appropriate metadata and keywords so that if someone was searching for an experimental data set related to attentional control, and I had that in my abstract, Google would be able to crawl it and it would become a search result for them. I can also make that same data available related to attentional control and just literally upload a CSV and call it file.csv. That's not findable. It doesn't have any metadata that would allow me to use code or search tools to find it. I need to know exactly where I'm looking, and somebody probably needs to also provide me a link so that I can find that information. So when data is findable, it has metadata and it's easily discoverable by search features like Google search algorithm. So data is accessible when people know exactly what they need to do to get access to the data. So if you have, for example, a system where somebody needs to fill out a concept proposal, describe to you why they want the data, and then they need to submit it somewhere, and then someone else needs to approve it. But if you go on that website to get the data and it doesn't say any of that, the data is not accessible. You know, as the data provider, that that's your process, but the data user doesn't know that there's a process to work with that data. And so it exists, and you're happy to make it available with this process, but you're not making clear that you have a process so people don't know how exactly to go about it. And that could be things like authentication as well. You might have it publicly available, but it's not clear that they need to register for an account first. And so making data accessible is documenting the process by where people get access to that data. Data is interoperable when you can integrate it with other workflows. So just as an example, if you have SPSS data, you need certain packages in R or certain packages in Python to read it. But let's say those packages didn't exist. That data can only live inside of SPSS. And so it's no longer interoperable because you need the SPSS software and license yearly to be able to use that, as opposed to being able to open that file in any old text editor and see the contents. And so often what interoperable data means is that you're saving your data as a text file, as a CSV file, worst case scenario, an Excel file, but ideally something that anyone can open without a paid software. And then last, it's the idea that data should be reusable. So if I found value in data from 500 people that took part in an attentional control experiment, I should provide enough metadata that someone can understand the value and realize where they can reuse this data for their own work. Somebody might be able to write a dissertation or work out a data science project from that data, but they only could do that if I express to them all the applications of this data, what are its limitations, what are its strengths. And so making data reusable is more so a high level process where you're explaining the whys and explaining where you get data and its metadata so that people know if they wanted to do something, how they would go about it and how they would talk about it and communicate those results.